Welcome! In this session, we'll dive into LeetCode problem number 1991, titled Find the Middle Index in Array. This problem focuses on identifying an index in an array where the sum of elements on the left equals the sum of elements on the right. It's a great way to practice problem-solving skills with arrays and basic arithmetic operations. Let's get started. In this problem, we need to find the middle index in a given integer array nums. A middle index is defined as an index where the sum of all elements to the left of the index is equal to the sum of all elements to the right of the index. Note that the left sum does not include the element at the middle index itself, and similarly, the right sum does not include the middle index. If there are multiple indices that satisfy this condition, we are required to return the leftmost one. If no such index exists, we should return -1. The input array nums has a length between 1 and 100, and each element in the array is an integer between -1000 and 1000. The output should be a single integer, representing the leftmost middle index or -1 if no valid index is found. Let's look at an example to understand this better. Suppose the input array is nums equals 2, 3, -1, 8, 4. Here, the output is 3. To see why, consider index 3. The sum of elements to the left of index 3 is 2 plus 3 1, which equals 4. The sum of elements to the right of index 3 is simply 4. Since the left sum equals the right sum, index 3 satisfies the condition of being a middle index. Now take another input, nums equals 1, -1, 4, where the output is 2. For index 2, the left sum, which is 1 plus -1, equals 0, and the right sum is also 0. This means index 2 is a valid middle index. In another example, if the input array is nums equals 2, 5, the output is -1. Here, there is no index where the left sum equals the right sum. This means no valid middle index exists in this case, so the correct answer is -1. These examples illustrate how the sums on both sides of an index determine whether it qualifies as a middle index. It's important to note that we should always return the leftmost index if multiple middle indices are valid. Let's now consider some edge cases. First, if the array contains only one element, that element is trivially the middle index because there are no elements on either side. For example, in nums equals 4, the output is 0. Next, if the array consists entirely of zeros, such as nums equals 0, 0, 0, every index qualifies as a middle index. Per the problem requirements, we return the leftmost index, so the output is 0. Another edge case is when no index satisfies the condition, such as in nums equals 1, 2, 3, where the output is -1. Finally, negative numbers do not affect the logic but can influence the sums. For instance, in nums equals -2, 1, -1, 2, the output is 2 because index 2 balances both sides. These constraints and edge cases ensure that the solution is robust and handles a variety of inputs appropriately. To solve the problem of finding the middle index in an array, we start by understanding the task. The objective is to locate an index I where the sum of elements to the left of I equals the sum of elements to the right of I. If no such index exists, we return -1. One way to approach this is through a brute force method. The idea is straightforward. For every index I, we calculate the sum of all elements before I, the left sum, and the sum of all elements after I, the right sum. We then compare these two sums. If they are equal, we return the index. While this approach is intuitive, it requires recalculating sums for each index, leading to a time complexity of n squared. This quadratic complexity makes the brute force solution inefficient for large arrays. However, the simplicity of the approach ensures it is easy to grasp and implement, though not practical for competitive programming or real-world scenarios. A more efficient solution can be achieved using the prefix sum technique. The key insight here is that we do not need to repeatedly calculate the left and right sums for every index. Instead, we can derive the right sum using a simple formula: right_sum equals total_sum minus left_sum minus the value at the current index, nums, I. Here, total_sum represents the sum of all elements in the array, and left_sum is the cumulative sum of elements to the left of the current index. For a valid middle index, the condition left_sum equals right_sum must hold. Using this approach, we can solve the problem in a single pass through the array. The process involves first computing total_sum, initializing left_sum to 0, and then iterating through the array. At each step, we check the condition. If it is satisfied, we return the current index. Otherwise, we update left_sum by adding the current element. If no valid index is found by the end of the iteration, we return -1. This approach eliminates the inefficiencies of the brute force method while maintaining simplicity. The prefix sum technique offers a significant improvement in both time and space complexity. With a single pass through the array, the time complexity is reduced to O(n), making it linear. Additionally, since no extra data structures are required, the space complexity remains constant, or O(1). This makes the prefix sum approach the optimal strategy for solving this problem. The key breakthrough lies in recognizing that the right sum can be derived directly from the total sum and the left sum, avoiding redundant computations. This insight shifts the problem from a quadratic complexity solution to a linear one. The prefix sum approach is not only efficient but also simple to implement, as it avoids nested loops. It is scalable, capable of handling large inputs efficiently, and strikes the perfect balance between performance and ease of understanding. While the brute force approach may be easier to grasp initially, it is far less practical for larger datasets, where the prefix sum method excels. The prefix sum approach is ideal for competitive programming and real-world applications due to its efficiency and practicality. While it requires understanding the concept of cumulative sums, this additional complexity is minimal compared to the performance gains. No alternative solutions are necessary in this case, as the prefix sum method already achieves optimal results. It balances performance, simplicity, and scalability, making it the best choice for solving problem number 1991. In summary, this approach ensures that the task is completed in the most efficient manner possible, even for large arrays, while remaining straightforward to implement and understand. This is why the prefix sum technique stands out as the definitive solution for finding the middle index in an array. This problem asks us to determine a special index in an integer array where the sum of elements to its left equals the sum of elements to its right. This index is called the middle index, and if no such index exists, we return -1. To achieve this, we need to first understand the concept of left and right sums. The left sum at an index is the sum of all elements before it, while the right sum is the sum of all elements after it. Our task is to identify the first index where these two sums are equal. To solve this efficiently, the prefix sum technique comes into play. This involves calculating the total sum of the array, iterating through the elements while maintaining a running left sum, and dynamically computing the right sum for each index. By comparing these sums, we can determine if the current index satisfies the condition. If it does, we return that index, otherwise, we return -1. To implement the algorithm, we first calculate the total sum of the array, which gives us a reference point for the right sum calculations. We then initialize the left sum to 0. As we iterate through the array, we compute the right sum dynamically using the formula right_sum equals total_sum minus left_sum minus the current element. If the left sum equals the right sum at any index, we return that index immediately. If not, the left sum is updated by adding the current element to it, and we continue to the next index. If no such index is found after the entire iteration, we return -1. This approach minimizes redundant calculations and ensures an efficient solution. The key here is using the prefix sum technique to eliminate the need for nested loops, which would otherwise result in a less efficient brute force approach. This algorithm is built on several key insights. First, the use of the formula for calculating the right sum dynamically prevents the need for recalculating sums in nested loops, reducing the overall time complexity to O(n). Second, the one-pass iteration ensures that we traverse the array only once, maintaining efficiency even for large input sizes. Third, handling edge cases is crucial. For example, if the array is empty, we should return -1 by default. If the array contains only one element, the middle index is 0, since there are no elements on either side. The algorithm also handles negative numbers seamlessly, as the calculations are consistent regardless of the sign of the elements. These insights demonstrate the robustness and efficiency of the solution. Additionally, the algorithm uses minimal space, relying only on the input array and a few variables for computation. The right sum is calculated dynamically during the iteration, ensuring that we do not need additional space or nested loops. This leads us to the time and space complexity analysis. The time complexity of the algorithm is O(n), where n is the length of the array. This is because we calculate the total sum in O(n), and then iterate through the array once in O(n). The space complexity is O(1), as we use only a constant amount of additional space, namely, variables for the total sum, left sum, and the dynamically computed right sum. Let's consider an example to solidify this understanding. Suppose the input array is nums equals 2, 3, -1, 8, 4. We start by calculating the total sum, which is 16, and initialize the left sum to 0. As we iterate through the array, we calculate the right sum dynamically and compare it with the left sum at each step. For the first element, at index 0, the right sum is calculated as 14, which does not match the left sum of 0. We then update the left sum to 2 and move to the next index. At index 1, the right sum becomes 11, while the left sum is now 2. Again, they do not match, so we update the left sum to 5. At index 2, the right sum becomes 12, and the left sum is 5. Still no match. We proceed to index 3, where the right sum is calculated as 4, which finally matches the left sum of 4. This means index 3 is the middle index, so we return 3. If no index had satisfied the condition, the algorithm would return -1. This example demonstrates how the algorithm dynamically calculates and compares sums at each step, ensuring efficiency and correctness. In conclusion, the prefix sum approach provides an optimal solution to the problem of finding the middle index in an array. By leveraging dynamic calculations of the right sum and maintaining a running left sum, the algorithm achieves O(n) time complexity with O(1) space complexity. This makes it well suited for handling large arrays efficiently. The solution is robust, addressing edge cases such as empty arrays, single-element arrays, and arrays with negative numbers. By minimizing redundant computations and focusing on a single traversal of the input array, this method ensures both clarity and performance. With these insights, we can confidently apply this approach to solve the problem in an efficient and elegant manner. This solution to LeetCode problem number 1991, find the middle index in array, efficiently determines the middle index in the array by iterating through it just once. First, the total sum of the array is calculated using Python's built-in sum function. This value allows us to derive the right sum dynamically during the iteration. We also initialize a left_sum variable to 0, which will keep track of the cumulative sum of elements to the left of the current index. The algorithm then loops through the array using a for loop. For each index I, the right sum is computed as total_sum left_sum nums I. This calculation ensures that the right sum reflects the sum of elements after the current index. If the left_sum equals right_sum, the function immediately returns the current index I, as it satisfies the desired condition. If the condition is not met, the left_sum is updated by adding the current element nums I to its value. This ensures that the left_sum remains accurate for the next iteration. If the loop completes without finding a valid middle index, the function returns -1, indicating that no such index exists. This algorithm runs in O(n) time, as it involves a single traversal of the array, and uses O(1) additional space, making it both efficient and concise. Overall, the solution is optimized for performance and handles all edge cases, such as empty arrays or arrays where no middle index exists. This is the Java implementation of LeetCode problem number 1991, find the middle index in array. The logic mirrors the provided Python solution, with adjustments for Java syntax and conventions. Key differences include explicit type declarations, use of Java's enhanced for loop for summing elements, and the absence of Python's built-in functions like sum. The solution iterates through the array to calculate the left and right sums, returning the index where they are equal or -1 if no such index exists. To solve the problem of finding the middle index of the array, we begin by looking at example 1 with nums equal to 2, 3, -1, 8, 4. First, we calculate the total sum of the array. Adding all the elements together gives us a total_sum of 16. We also initialize left_sum as 0, which will keep track of the sum of elements to the left of the current index as we iterate through the array. Now, we start iterating over the array. In the first iteration, where I equals 0, nums, I, is 2. We calculate right underscore sum as total underscore sum minus left underscore sum minus nums, I, which is 16 minus 0 minus 2, resulting in 14. At this point, we check if left underscore sum equals right underscore sum. Since 0 is not equal to 14, we proceed by updating left underscore sum to include nums, I. So left underscore sum becomes 0 plus 2, which is 2. Next, in iteration 1, where I equals 1, nums, I, is 3. Here, right underscore sum is calculated as 16 minus 2 minus 3, resulting in 11. Again, left underscore sum and right underscore sum are not equal, so we update left underscore sum to include nums, I, making left underscore sum 2 plus 3, which is 5. Continuing with the iterations, in iteration 2, where I equals 2, nums, I, is minus 1. We calculate right underscore sum as 16 minus 5 minus minus 1, which simplifies to 16 minus 5 plus 1, resulting in 12. Once again, left underscore sum and right underscore sum are not equal, so we update left underscore sum to include nums, I. This makes left underscore sum 5 plus minus 1, which is 4. Now, in iteration 3, where I equals 3, nums, I, is 8. The right underscore sum is calculated as 16 minus 4 minus 8, which is 4. At this point, left underscore sum equals right underscore sum, as both are 4. Since the condition is met, we return I, which is 3. The final output for this example is 3. In example 2, the nums array is 1, minus 1, 4. First, we calculate total underscore sum by adding the elements together, resulting in 4. We initialize left underscore sum as 0. Then, we begin iterating through the array. In iteration 0, where I equals 0, nums, I, is 1. The right underscore sum is calculated as 4 minus 0 minus 1, which is 3. Since left underscore sum is not equal to right underscore sum, we update left underscore sum by adding nums, I, making left underscore sum 0 plus 1, which is 1. Next, in iteration 1, where I equals 1, nums, I, is minus 1. Here, right underscore sum is calculated as 4 minus 1 minus minus 1, which simplifies to 4 minus 1 plus 1, resulting in 2. Again, left underscore sum and right underscore sum are not equal, so we update left underscore sum to include nums, I. This makes left underscore sum 1 plus minus 1, which is 0. Finally, in iteration 2, where I equals 2, nums, I, is 4. The right underscore sum is calculated as 4 minus 0 minus 4, which is 0. At this point, left underscore sum equals right underscore sum, as both are 0. Since the condition is satisfied, we return I, which is 2. The final output for this example is 2. Now, let's look at example 3, where the nums array is 1, 2, 3. We start by calculating the total underscore sum, which is the sum of all elements. 1 plus 2 plus 3 equals 6. We initialize left underscore sum as 0. Next, we iterate over the array. In iteration 0, where I equals 0, nums, I, is 1. The right underscore sum is calculated as 6 minus 0 minus 1, which is 5. Since left underscore sum is not equal to right underscore sum, we update left underscore sum by adding nums, I, making left underscore sum 0 plus 1, which is 1. In iteration 1, where I equals 1, nums, I, is 2. Here, right underscore sum is calculated as 6 minus 1 minus 2, which is 3. Again, left underscore sum and right underscore sum are not equal, so we update left underscore sum to include nums, I. This makes left underscore sum 1 plus 2, which is 3. Finally, in iteration 2, where I equals 2, nums, I, is 3. The right underscore sum is calculated as 6 minus 3 minus 3, which is 0. At this point, left underscore sum does not equal right underscore sum, as 3 is not equal to 0. Since we have completed the iterations without finding a valid index, the output for this example is minus 1. To summarize, this solution efficiently finds the middle index by using a single pass through the array. At each step, we calculate the right sum dynamically by subtracting the current left sum and the current element from the total sum, while updating the left sum as we go. The algorithm operates with a time complexity of O(n), where n is the length of the array, and it uses constant space, making it both efficient and simple to implement. The time complexity of our solution is O, n, where n is the number of elements in the input array. To break this down, the first operation is calculating the total sum of the array using the sum function, which requires iterating through all n elements, making it O, n. Next, during the single iteration through the array, the right sum is computed using the total sum, left sum, and the current element. Since this involves basic addition and subtraction, each calculation is a constant time operation, O1. Similarly, the comparison between the left sum and right sum is also O1, as is updating the left sum by adding the current element. Since the loop runs once for each element, this contributes an additional O(n). Combining the O(n) from calculating the total sum and the O(n) for the loop gives us an overall time complexity of O(n). Now, let's analyze the best, average, and worst cases for this solution. In the best case scenario, the algorithm identifies the middle index on the very first iteration, at index 0. However, the total sum of the array still has to be calculated beforehand, which takes O(n), therefore, the best case time complexity remains O(n). For the average and worst cases, the algorithm must iterate through the entire array to check each index, which also results in O(n). Moving on to space complexity, the solution is highly efficient, with a space complexity of O(1). This is because the algorithm does not require any additional data structures or space proportional to the size of the input array. Instead, it uses a few scalar variables, total_sum, left_sum, and right_sum, all of which occupy a fixed amount of memory regardless of the input size. Thus, the space complexity remains constant, O(1). To better understand the efficiency of this solution, let's compare it to a naive or brute force approach. In a naive approach, for each index in the array, we would calculate the left sum by summing all elements from the start of the array up to that index, and the right sum by summing all elements from the index to the end of the array. Calculating the left sum for a single index takes O(i) time, while calculating the right sum takes O(n)i) time. Repeating this process for all n indices results in a total time complexity of O(n squared). In contrast, the optimized solution avoids the need to recalculate sums repeatedly by pre-computing the total sum of the array and maintaining a running left sum. This allows the right sum to be derived in constant time, reducing the time complexity from O(n squared to O(n). Finally, let's solidify our understanding with a mathematical proof of the big O complexity. The optimized solution performs two main operations. First, it makes a single pass over the array to compute the total sum, which is O(n). Second, it makes another pass to iterate through the array, performing constant time operations at each step, such as updating the left sum, calculating the right sum, and performing comparisons, all of which contribute O(1) per iteration. Adding these two O(n) operations together, the total time complexity is O(n) plus O(n), which simplifies to O(n). As for space complexity, the solution does not use any additional space beyond a few scalar variables, regardless of the input size, resulting in a constant O(1) space complexity. This demonstrates that the algorithm is both time efficient and space efficient, making it well suited for handling large inputs. When working on this problem, there are a few common mistakes to watch out for. First, incorrect index handling can trip you up. Remember, the left sum should exclude the element at index I, so comparing sum nums I to sum nums I plus 1 without properly excluding nums I will lead to wrong results. Then there's the inefficiency of brute force. If you use a nested loop to calculate the left and right sums for each index, you'll end up with a time complexity of O(n squared, which is impractical for large arrays and can trigger time limit exceeded errors. Another pitfall is off-by-one errors, especially in languages like Python, where array slicing can sometimes be confusing. For instance, nums I excludes nums I, but nums I plus 1 starts right after index I. Always double-check your ranges. And don't ignore edge cases. Arrays with a single element, empty arrays, or arrays where all elements are 0 can cause runtime errors or incorrect results if not handled properly. Lastly, don't assume every input will have a solution. If no valid middle index exists, the problem specifies that you should return -1, so ensure you handle this scenario explicitly. Now, from an interview perspective, this problem offers valuable insights into optimization techniques. The prefix sum pattern is a critical concept here. By pre-computing the total sum of the array, you can iterate through the elements and calculate the left and right sums dynamically in O(n) time. This eliminates the inefficiency of recalculating sums repeatedly, which is key to scalability. Additionally, handling edge cases is an important part of interview discussions. Always take the initiative to clarify input constraints. For example, you might ask whether the input array can be empty or if it includes negative numbers. These questions show that you're thinking about robustness. Finally, when presenting your solution, explain the trade-offs clearly. Compare the brute force approach to the optimized solution, emphasizing how the latter reduces time complexity and scales better for large inputs. This demonstrates your understanding of algorithmic efficiency and practical problem solving. Looking at related problems can deepen your understanding and expand your toolkit. For instance, LeetCode 724, the pivot index problem, is very similar but allows the pivot element to be part of both the left and right sums. LeetCode 53, maximum subarray, uses prefix sum concepts to find the maximum sum of a contiguous subarray. Then there's LeetCode 238, product of array except self, which applies a similar prefix product approach but avoids division. Finally, LeetCode 560, subarray sum equals k, is another prefix sum problem but focuses on counting subarray sums that match a given target. Now, when it comes to alternative approaches, brute force is the most straightforward but inefficient method. It involves iterating through all indices and calculating the left and right sums directly, which results in O(n) squared complexity. A better approach is using prefix sums. By pre-computing the total sum, you can iterate through the array once, dynamically updating the left sum and deriving the right sum as total_sum left_sum nums, I. This method is efficient, with O(n) time complexity and O(1) space. Another option is the two-pointer approach, which maintains left and right sums while adjusting pointers. While it's less common for this specific problem and more complex to implement, it can still be a viable alternative in some scenarios. Thank you for joining me in solving LeetCode problem number 1991, find the middle index in array. We covered the problem requirements, efficient approaches, and key takeaways to enhance your problem-solving skills. Don't forget to practice similar problems to strengthen your understanding of array manipulation. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!